Next topic, the BiFunction. So as you'll see, BiFunction is pretty much like function with one subtle difference. It adds a second function. That's why it's a BiFunction. It's got it adds a second parameter. It has two parameters instead of one. So BiFunction is a functional interface. As you can see, it takes 3 parameters. It takes t, which is the first parameter to apply, u, which is the second parameter to apply, and r, which is the return value. Apply for BiFunction is like apply for function, except there's a second parameter, not just a single parameter. And it also returns a return value of type r. Let's use our stoogemap again, just for kicks. So here's the stoogemap, Larry, Curly, and Moe. Except this time we're going to do something a little different. This time what we're going to do is we're going to compare and contrast 2 alternative ways for subtracting a certain amount of IQ points from each value for each stooge in the map. So you can see we're going to have a map which iterates from the beginning of the entry set to the end, however it's structured. And in this version, which is not using any Java 8 features, we're going to set the value of each entry in the map to the current value minus 50. So that's the kind of conventional way of subtracting 50 IQ points from each stooge in the map. And this is just showing a classic for each loop. So we're going to get the entry set, and we're going to iterate through that entry set. Each entry in the entry set is an entry, or each element in the entry set is an entry mapping string to integer or stooge to their IQ. And this is the kind of the old school way of doing things. There's several limitations with this way. Number one, it's kind of verbose. And number two, it's not thread safe. So what do we do instead? Java 8 defines a replaceall method, which is defined on concurrent hash map. And what this does is this will go through the map using a BiFunction lambda for key and value. And it basically reads, for each key and value pair in this map, replace the value by subtracting 50 from the current value. So for the current value, take the current value, subtract 50, and that becomes the new value. So that's what replaceall does. So there's a couple of benefits here. It's very concise, for one thing. The other cool thing is that unlike this Java for each loop implementation, replaceall is an atomic operation. So it'll make sure that these changes occur in a way that will not be corrupted with race conditions. So it'll ensure atomicity, it'll ensure the ordering, and it'll ensure visibility. So all the key properties of concurrent thread safety will be preserved by replaceall, whereas that would not have been the case with this code. Plus, this code is just more verbose. Here's what replaceall looks like. As you can see, it's passed a BiFunction, which oddly enough is called function. It should be called BiFunction, but the parameter is called function, but it's a BiFunction. And you can see what it's going to do is it's going to iterate through the map. And as it goes through the map, it's going to apply the BiFunction with the current key and the old value. And it's going to create the new value, and it's going to replace the old value with the new value. So that's what it's going to do. And how does it work? Here's the lambda expression that gets bound to that function, or to that BiFunction. And you can see that when we say function.apply, or when the implementation says function.apply, what that's doing is that's going to basically say old value minus 50 equals new value, which then gets updated in the map in an atomic and efficient way. So pretty cool, much more concise than the other approach. Yes? So the question is, why does replace node take the old value? If you were to look at the way that, so the question is, well, why does it not just look it up? Well, you wouldn't want to go through the trouble of looking it up again when you already have it. So looking something up in a map takes time. And what replace node does most likely, I'm willing to bet, is it's going to do some kind of clever compare and swap operation on this thing to do a wait-free and lock-free update of old value with new value. We'll talk a bit more about that. That'll actually be covered a bit more in my other class in the spring when we talk about compare and swap operations, but they can make it really, really efficient. But the main reason is they don't want to have to look it up again in the map. Because once you've got it, why not just use it? OK, so